Let's learn about vectors and scalars in this video. This is one of the fundamental topics in physics and maths. In the natural world, we can find many different physical quantities. Some examples include all these physical quantities we can classify broadly into two categories, which are scalars and vectors. So what is the criteria for classifying the quantities into two broad categories? So some of these quantities, time, temperature, mass, speed, etc., just require magnitude to make complete sense of it. Of course, we need a unit for all these quantities. So in addition to that, we just need the magnitude. So for example, if I'm talking about time, I can say, okay, 10 seconds makes complete sense. And temperature, 5 degrees Fahrenheit or 5 degrees Celsius. That makes sense. And when I'm talking about mass, I can say 10 kilogram as the mass of the object. That makes complete sense. So, but certain other quantities such as position, velocity, force require magnitude as well as the direction to make complete sense of it. So, for example, if I'm talking about the position, if I draw a dot in here and if someone else is asking me to put another dot at 5 centimeters away from it, I'm completely lost because there are many different points at 5 centimeters away from it. So, to make complete sense of it, I need 5 centimeters, that's a magnitude, plus a direction. So, for example, if I'm asked to put a dot at 5 centimeters to the right, I'm confident in putting it here. And 5 centimeters to the top, I can do it here. So, such quantities are known as vectors. So, scalars are the quantities that require magnitude only plus a unit. And some other examples are distance, time, volume, speed, temperature, etc. are some other examples. And vectors require magnitude as well as the direction to make complete sense of that physical quantity. Okay. Other examples include position, displacement, velocity, force, acceleration, etc. are some other examples. Suppose we have three force vectors F1, F2 and F3, all with different magnitude and directions. How can we properly represent these vectors? So first of all, these arrows are showing this is a vector. So that's a usual practice to use either an arrow or use a bold letter. But it's always easy to put an arrow rather than using the bold letters. Okay. And to represent these vectors, we can use a vector diagram. So that's usually an arrow. It's very simple. Use an arrow. And if I'm representing 1 Newton to the right, so what I can do is draw a vector, draw an arrow like this, 1 Newton to the right. Okay, so the length of the arrow shows the magnitude, whereas the arrowhead is showing the direction from tail to head. So that's the direction. Okay, so F1 is represented as 1 Newton to the right. So when you represent the second vector, F2 equals 2 Newton to the right, the magnitude is twice and the direction is opposite. So the arrow should be pointing in the opposite direction and should have twice the magnitude. So the length of the vector should be twice as length of this one, should be scaled appropriately to represent the magnitude accurately. Okay, so the length should be twice and pointing to the left. So it's F2 equals 2 Newton. And the third vector F3, 3 Newton upwards, the length should be thrice this one and arrow should point upwards. So that's something 1, 2, 3. So that's 3 Newton upwards. Okay. So this is how we represent vectors appropriately using the arrow. The length of the arrow shows the magnitude and the direction is given by the arrowhead. The simplest kind of vectors is vectors in one dimension. If there's only one dimension possible, we can have only two directions. Okay, so for example, if it's a horizontal dimension, you can have this direction or opposite direction. So you can say this is a right direction and this is left. So if I'm talking about motion in one dimension along the horizontal plane or along the horizontal dimension, I can say, okay, 3 Newton to the right or 2 Newton to left. It's very easy in the case of one dimension. Or if it's upwards and downwards, you can say this is upwards and this is downwards. This is upwards and downwards. Many other possibilities are also there. So you can use, instead of upwards, you can use north and south, or in right and left you can say forwards and backwards, or you can say east and west. So different combinations are possible. So another thing you can do in case of one-dimensional vectors is attaching a sign convention. There's only two directions possible. So if we take one direction as positive, the other direction can be taken as negative. So for example, in here, I could possibly choose right as positive, and then the opposite direction left is negative. It's quite arbitrary to choose which one positive and which one negative, but if you choose one positive, the other one is negative, and stick with that throughout the problem. Okay, so if I'm choosing upwards as positive, it's not necessary that I should choose upwards as positive. So possibly I could choose downwards as positive, and then upwards is negative. So if I'm talking 3 meter upwards, I can say minus 3 meter. 3 meter upwards is minus 3 meter. So the physical direction is changed to a mathematical sign. The beauty is you can then enter this into the calculator, where this direction upwards you can't. Okay, so in this case, if I'm taking an example in here, if I'm saying 5 Newton to the right, I can say plus 5 Newton. And if I'm taking 3 Newton to the left, I can say minus 3 Newton. Okay, so physical direction is converted to a mathematical sign, and the calculations become really simple. So whenever you use a sign convention in a problem, you should remember to provide the key explaining the sign convention in the problem. Something like this one, left is negative, right is positive, something like that.